Hello everyone. So this is the beginning of Math 204 and we are going to study complex variables, and hopefully later we'll talk about something called a Riemann surface and all that. But the very starting point is to understand what is a complex number. To answer this question, first we need to find out something called an imaginary unit, and after that we can introduce the complex number. So before we start answering this question over here, we want to ask another question, and that is the question of imaginary numbers. So far we have only dealt with real numbers, then comes the imaginary number, and finally you will have your complex numbers and all that. So before we give a formal definition, let's consider an equation that's something like this: x squared plus 1 equals to 0, and we want to find out the solutions for this x. So what is the solution for x? As you can see that if you want to do the algebra, you would write this as x squared plus 1 equals to 0, and then you would say x squared equals to minus 1, something like this. And if you restrict that x should be only a real number, then you can easily see that if this is true, then there is no x that satisfies this equation. That means in the real number domain you cannot find any number that you take the square, then you plus 1, and then it becomes 0. This is not possible. So what if we ease this restriction a little bit? That means it doesn't have to, that means this x doesn't have to belong in the real number set, it can be anything. So we are removing this constraint of this real number set and all that. So if we do that, we will find ourselves with a situation where we will have x is equals to plus minus square root over minus 1, right? And if you plug this back into this equation, it's the solution, as you can see, because this guy will satisfy this equation over here. So this is one way to realize how imaginary numbers comes into play. So now let's give a formal definition of the imaginary number. So the imaginary number, or the imaginary unit I should say, imaginary unit is defined as the following, and this notation is due to Euler. That is, there is this I, that means the imaginary unit, and if you take I square, this is just minus 1. So technically you can think of this imaginary unit as a square root over minus 1. And when you do that, you can define some new numbers. Let's say there is a number called z1, and let's define this number as 2 plus 3i. As you can see, it has two parts. This one, 2, this belongs to the real numbers set, and there is this 3 itself is a real number, however there is a imaginary unit multiplied with it, and this whole thing, this z1, that is a composite of a real number and a imaginary unit times some other real number, is known as a complex number. And if you consider a set where you have numbers like this, where a and b, all of them belongs to real number, then all the numbers that make up this set will be called a complex number set, defined as this. So this is how complex number comes into play. And in fact, if you write a complex number like this, a plus ib, then a is called the real part of z, also written like this, re of z equals to a, and b is called the imaginary part. of z, written as Im, that means imaginary, z equals to b. Now, if you are familiar with vector analysis, that means from your high schools you have known that vector is something that has a magnitude and a direction, and let's say there is some vector v that is written as 3x hat plus 2y hat. You would easily recognize this as a vector in the xy plane that has a 3 as a x component and 2 as its y component. So this is y and this is x, and it should be something like this. And you can see that this is pretty similar to this formation. So in the real number line you have the unit as 1, right? This 1 is the unit. With this unit you can build up any real number. So instead of a, you can always think of it as a times 1. And in the imaginary unit there is this I, and with I you can build up any imaginary number. So you can think of these numbers as a vector as well. So if we consider that, then we can try to put them in a plane, and that is known as the complex plane. So how does this complex plane looks like? Let's indicate the imaginary axis with this green color, and let's mark the real axis with this bluish color. And if you consider a number, let's say z is equals to 2 plus 3i, this tells you that to find this number denoted by, let's say, z1, you have to go 2 units into the real line and 3 units into the imaginary line. That means this imaginary unit, this green line over here, let's say this is 1 unit, so it should be I. This is 2 units, so it should be 2i. This point represents 3 unit, so 3i, and so on. And let's say this is 1, 2, 3, 4, and so on. So this is 2. So first you start from the origin or the 0, 0 coordinates, then you go to 2, and then you move into the y direction, or let's say the positive y direction, and you have to move like 3 units, 1 unit, 2 unit, 3 unit, and there it is. This is the number 2 plus 3i. And as you can see, just like a vector, you can denote this number with an arrow if you want. And similarly, let's say minus 2 minus 5i. So minus 2 would be somewhere over here, minus 5i would be somewhere over here. So this should be something like this. And let's say this is a 2. How about another number? Let's say this is 3 minus 6i. So you have to go over here for positive 3, and then minus 6i would be somewhere down here. So this should be your z3, so on and so forth, just like vectors. Now you may ask, okay, since we are comparing these complex numbers with vectors, we know that vectors have a magnitude and a direction. So can we define something similar for complex numbers? Well, the answer is yes, because as you can see from this graph over here, from the origin all of these numbers have some distance. So maybe there is a way we can find out what is that distance, and it's pretty simple. It's as simple as just doing the dot product in the vector case. But since we're doing complex numbers, we don't want to do all of these things with analogy. Rather, we want to define some other things, and then we will compare and contrast with the vector cases. So now what we want to do is that we want to find out a distance. At least we want to see whether we can find out a distance from the origin of a complex number. So to do that, let us define another thing. It's called a conjugate of a complex number. Conjugate, or complex conjugate to be more appropriate. Complex conjugate of a complex number. Okay. So if you have any complex number z that is written as x plus iy or a plus ib, whatever, then the complex conjugate is defined as, let me write that down properly. For any complex number number z, the complex conjugate of z is denoted by z bar, this bar thing, and z bar is defined as z bar equals to x minus iy. So our z was x plus iy, and the z bar, the complex conjugate, is also another complex number, and this is defined as x minus iy. And now, before we move on, I want to discuss some algebraic properties of complex number as well. We will come back to the distance thing a little later. So some algebraic, I should say some basic algebraic properties. So the first thing is very natural, and it's called an addition. So let's say you have two complex numbers, z1 as x1 plus iy1, z2 as x2 plus iy2, and you want to add them, right? Since we are comparing these two things with vectors, you can easily recognize that in vectors, if you had two vectors that had, let's say, one of them had a x component of 3, another had an x component of 2, so you would add the x component separately, the y component separately, and then the z component separately, so on and so forth. The same case, we will see that the same case will reappear here, but there is another subtlety, that is, these numbers are actually written in terms of ordered pair, like this. You can also write it like this. And when you have these ordered pairs and you want to add them, the rule is to maintain that order when you add them as well, or subtract them, because subtracting is just reverse addition type of thing. So if you do that, this is just x1 plus x2, y1 plus y2, and if you want to write it down in its full glory with the units, this would be x1 plus x2 plus I, y1 plus y2, and x and y, x1, x2, y1, y2, all of them belongs to the real number set. Same rules go for subtraction as well. So if you just put a plus minus over here, that's it, we are done. Addition and subtraction. They don't have to be positive, this x and y's, they can be anything as long as they're real. Okay, now there comes the multiplication part. Multiplication of complex number is just as similar as multiplying real numbers. If you have a complex number, let's say z, and it's written as, z1, which is written as x1 plus iy1, z2 as x2 plus iy2, we want to have z1 and z2. We want to define this multiplication, and first we write them down like this, x2 plus iy2, and you will see that this is just multiplying things like a plus b with c plus d, your usual algebra. So if you multiply, this will be x1 x2 plus iy2 x1 plus iy2 x2 plus I squared y2, sorry, this should be y1 y2, yeah, this should be y1 over here as well, index mistake. And then if you simplify and put I square equals to -1, then you'll have x1 x2 minus y1 y2 plus I x1 y2 plus x2 y1. Here I'm just collecting the real parts and the imaginary parts together. This is it. This is how multiplication is done in terms of complex numbers. And then we have the part that is called the division. So the division is a bit tricky. Let me show you why. So first think of a vector like this. Let's say there is a vector 2x hat plus 3y hat. And if you want to divide this vector by 5, then this is simply 2 by 5 x hat, 3 by 5 y hat. But if I tell you that there is another vector, let's say w, this is x hat plus y hat, right? And I want you to find out something like this. Does this make any sense? No. Because you cannot divide one vector by another. You can take their products, but you cannot divide them. So these are objects. These vectors, complex number, they're objects. And these objects are only divisible by scalars. And scalar, by scalar, I mean a number, a real number over here. Or an imaginary number, but not something composite. So just like this case, when you have a complex number, let's say z1 is equals to x1 I y1 and z2 x2 I y2, and you want to do this z1 divided by z2, you can write it like this: x1 plus I y1, x2 plus I y2. Now this division doesn't make any sense. Even though this is right, it still doesn't make any sense. Why? Because you have this complex number in the upstairs or in the numerator, but in the denominator you have the same kind of object, so you can't actually do that. So what we have to do right now, because so far we have only seen the divisions by scalars only, and that's the only kind of division that we can make sense of. So from a complex number over here, we want to extract either a real number or a complex number. That's what we want to do. We don't want any composite object. So the idea is to multiply the numerator and the denominator both with the complex conjugate of the denominator. So let me write it down. To carry out this division, we need to multiply z2 bar. So that's why I said the complex conjugate of the denominator. We need to multiply z2 bar in both numerator and denominator. Let's see how this turns out. So again, we are trying to divide these two things, z1 and z2, and we have x plus iy and we have x2 plus iy2, but we said we want to extract out a number in the denominator, so we want to multiply with z2 bar, and z2 bar is what? x2 minus iy2. So let's see what happens. And now if you multiply these two and these two, in the numerator you'll have x1 x2, then you'll have minus I y2 x1 plus I y1 x2 minus I squared y1 y2, and in the denominator you'll have x2 squared minus I y2 x2 plus I y2 x2, and finally you will have minus I squared y2 squared. So now what I'm going to do is that I'm going to simplify. That means I'm going to put a minus 1 in terms of I square, and I'm going to collect the real and imaginary parts in the both numerator and the denominator. And if you see closely that these two terms are equal and opposite to each other, so they cancel out. And this I square over here, we would replace it with a minus 1. Or we can equivalently write minus I square is equals to plus 1 as well. Whatever you like, because I square is defined as minus 1. So let's do that. And in the numerator we have x1, x2. There is I square and there's a minus. So we would have a plus y1, y2. And then let's collect the imaginary parts as well. I'm putting a plus I over here, so I will have x2 y1 minus x1 y2. And in the denominator we'll have x2 squared plus y2 squared. As you can see, this is a pure real number. That means this x2 squared plus y2 squared belongs to the real number. So finally you can write it as x1 x2 plus y1 y2 x2 squared plus y2 squared plus I x2 squared y2 squared x2 y1 minus x1 y2. Okay, because now everything seems fine. Why? Because you are dividing two complex numbers by each other, and the result is also another complex number in the same format. Because if you compare this guy with, let's say, some capital X1 and this guy with some capital Y1, then this is in the same format, just like any other complex numbers. So this would be written as x1 plus I capital Y1. So now let's get back to the distance business that we left a few minutes earlier. That is, we want to find out these distances that we kind of guessed from our earlier discussion and our analogy with vector. And this distance on the complex plane is called a modulus of a complex number. So now what are we going to discuss is that we're going to discuss the modulus of the complex number. And this is equivalent to the vector distance as well. Note that I'm saying it's equivalent. It's not the same exact thing. As you can see that if we have a complex number z1 and its complex conjugate like this, and if we multiply these two, that means z1 times z1 bar or z1 bar times z1, because these multiplications are commutative, you can easily prove that. You will have x1 square plus y1 square. And again, if you just make a short graph like this, the imaginary axis, the real axis, that means the x part and the y part, this x1 square and y1 square would be looking at this point something like this. This is just Pythagoras' theorem. That means this is our x1, this is y1, and this is just x1 squared, y1 squared, right? There should be a square root by Pythagoras' theorem. So this distance squared is something that is denoted with the x1 square plus y1 square. And now we define the modulus. That means we are taking a complex number and we are trying to find a modulus of it that is equivalent to a distance. What is that modulus? This is simply square root over x squared plus y square. That's it. That's the distance. And since we are comparing our complex number with vectors, you may ask, okay, is there something called a direction here as well? Well, there is something analogous to a direction as well, because notice that for many values of x and y, this thing can occur. Because if you draw a circle like this that has the same radius, all the complex numbers, let me denote it with another color, all the complex number that lies on the perimeter of the circle will have the same modulus. So how will you distinguish between these numbers? That means, let's say this one and this one. When I give you a modulus, I have to give you another piece of information, and that piece of information is called an argument of a complex number. And in layman's term, an argument is just the angle it makes with the positive x-axis, because when you define the modulus, that means you define the distance and you define the angle that is making with the positive x-axis. You have a unique description at the complex plane for that complex number. So now that we are done defining the modulus, let's define the argument. Argument of a complex number. So again, let me draw the graph. So this argument thing, initially it will look something like this. Let's say this is a complex number z1 that has this x and y components written down as x1 and iy1, and we want to find out this angle. So this is y1, this is x1, and as you can see, this is pretty easy. So we will write theta as tan inverse y by x, I mean y1 and x1, like this. This is the argument in simple terms, but there is an issue, because in the complex plane you can rotate and come back to this place again, or you can have a complex number that is on this place or on this place. So how do you define an argument then? Do you still define the argument to be an angle that is made with the positive x-axis or something else, right? So that's why there is a subdivision of an argument that is called a principal argument. And this principal argument, it's a bit confusing when you first see it, but there is a nice geometric interpretation of it. So argument is usually defined by the y and the x values of the complex number itself, but most of the time we are interested in something called a principal argument. And principal argument is always defined by this inequality, sum theta that lies between pi and minus pi. Why? Let's draw the graph again. I'm just calling it x and y right now. As you can see, x is just the real axis, y is the imaginary axis, and so on. So the principal argument actually tells you what is the minimum amount of angle you need to rotate from the x-axis, either in clockwise direction or in anti-clockwise direction, to reach a certain point of interest. It's like a geodesic, if you would say, on the theta direction. So let's say you have a point over here. There are many ways to go over there, right? You can, let's say this is path 1 denoted with the blue color. You can start rotating anti-clockwise direction, and let's say after some rotation, let's say some theta 1 value, you can get over here. And let's say there is another way that you start to rotate in the clockwise direction, and you have to rotate to an angle of theta 2 to reach this point over here. Now, which is the shortest, right? That's the thing. The shortest distance on this theta direction is the principal argument, and the reason the principal argument is bounded by this is because if you notice the upper half plane, let's call this the upper half plane, that means the plane on this side. Let me use another color to denote that. This is the upper half plane. and this is the, oops, they look like the same color, I guess, and this is the lower half plane. The only difference between these two, upper half plane and lower half plane, is that the coordinates itself. That means in the lower half plane the y is always negative and x can be positive or negative both, and in the upper half plane y is always positive where x can be positive and negative both. So in a sense, the lower half plane is nothing but the mirror image reflected on the, let's say the pivot is x, and you are reflecting the upper half plane, and you will get a lower half plane as well. So they are mirror reflections of each other, and that's why whether you rotate in anti-clockwise direction or clockwise direction, if you rotate in the clockwise direction in the upper half plane, your mirror image should rotate in clockwise direction in the lower half plane, so on and so forth. So that's why the principal argument serves as a geodesic. That means the shortest distance that you need to cover. So that's the geometric interpretation of it. Now we defined the principal argument like this. Now the question is, how do you calculate it? Well, there are some certain things to calculate the principal arguments. If you have, let's say this is your complex plane, this is the imaginary, or say the y-axis, this is the real or the x-axis, and let's say you have a point over here, z1 is equals to x1 plus iy1, and the shortest distance is what? This angle, right? Theta 1. So for z1, the argument, we will write it as small arg or capital Arg. It doesn't matter how you write it. All you have to do is to clarify your notation, that what is the argument, or is it the principal argument you're talking about, or is it something else. So this argument of z1, let's say the principal argument, since we're dealing with the principal argument only, it will be just tan inverse y by x, because this is the shortest distance, right? Now let's take another point that is on the second quadrant like this, and this is denoted by minus x2 plus iy2. Now how do we calculate the shortest distance? We can easily see that the shortest distance would be this guy, theta 2, right? And how do we calculate theta 2? If you see that from here, the positive x-axis to the negative x-axis, or so to say the positive real axis to the negative real axis, we have a total angle of pi in the anti-clockwise direction. And if we subtract some angle that is denoted as phi over here, we can get the theta 2, right? That's what we are after. So if you write it in short, it will be argument of z2 as pi minus tan inverse y2 by x2. You can obviously check it out geometrically as well. If you do the geometry, you can draw this triangle, then you determine this phi first, then you are saying this theta 2 is actually pi minus phi, then you put the value of phi in terms of y2 and x2, and finally you will have this expression. I'm just writing out it directly here. Similarly, if you have another number in this axis, let's say this is z3, and you can easily guess that here x3 is positive, however y3 is negative, right? So it has some formation of x3 minus iy3. And similarly, the shortest distance now would be to rotate in the clockwise direction like this, right? That should be the shortest or let's say the smallest rotation angle we can get to go to this point, the point z3. So in this case, z3, the principal argument would be minus pi. Why there is a minus pi? because you are rotating in the clockwise direction. So whenever you do a rotation, if you consider the clockwise direction as positive, then the anti-clockwise direction is negative. But in general, or let's say conventionally, the anti-clockwise direction is always positive and the clockwise direction is negative. That's how the orientation goes. So that's why you need a minus pi over here, because first you have to rotate anti-clockwise up to the negative real axis. I mean, sorry, not anti-clockwise but clockwise. So there is a angle of minus pi, and then you can do the geometry just like this one, the previous case, and you have to subtract that angle, and this will be just tan inverse y3 by x3. Note that while I'm writing these formulas, I'm not considering the signs of y's and x's. So this is a crucial thing to remember when you are using these formulas, or you can do it from the scratch. So let's say your z3 was something like how do you say it, minus 2. This should be minus, sorry, so it should be minus 2 minus 3i, right? Then when you apply this formula, or you want to find this argument of z3, the principal argument, it should be minus pi plus tan inverse 3 by 2. We are not considering the signs, because when we are doing the geometry, all the problems of the signs have been taken care of. And finally you can have another case, that is a point over here, that is a plus x and minus y component, and this is simple. This is just tan inverse, I mean, sorry, minus tan inverse, let me write that properly, argument of z4 is equals to minus tan inverse y4 by x4. And these are the things that you need to calculate the argument, that means the principal argument. So this will be it for this lecture, and in the next lecture we are going to see the polar form of complex numbers. So far what we have discussed in this lecture, you can see that this complex number, they possess a similarity with the Cartesian vectors, right? You have some x component and y component. In the next lecture we are going to see the polar representation, the exponential representation, and finally we will give off some definitions that we will be using when we define the functions of complex number and complex variables. Thank you.